Hi everyone, I'm Senan, and in this video we are going to see that how can you insert an element into a linked list. So this would comprise of only pseudocode, and in the next video I would be making the actual implementation, or I would write the code in C++ so that you can have a look. So let's talk about insertion. So when we talk about insertion, why do we need insertion in a linked list? And why do we need linked list in the first place? And the reason for that, when you use arrays, although you get the ability to have random access, the size of the array is always fixed. So you have to either create a new array, then copy all the elements, or you could use a linked list. Now the only demerit linked list has over the array is it requires a lot of space, twice the amount of space in general, because every node in a linked list would have a value and the next pointer. So because of this reason, as you would be having the next pointer, you would have to store this information. And that is all about linked list. So let's get started with insertion. There are three things we need to cover in this. The first one is inserting at head. That's the first one. Second one is inserting at tail, or the end of the list /end. And the third would be inserting at any position. So these three are the major cases, and that would complete your insertion in a linked list. Okay, so what I would be assuming that our node structure is like this. Node is like this. It would have an integer value. It would have a node star pointer, which is the next node, and that's it. That is our node structure. So it would look something like this. This would be our node, this would hold our value, and this would be the next pointer. Now I am using the word pointer, and if you're not aware of pointers or you're using Python, it's just another variable that would store the location of the next node. That is the only use of this pointer in this context. So let's start with number one, inserting at. So the thing is, if this video is going slow for you, you can just speed that up. So you have a linked list, right? Like this. Let's say you have a few more and something like this. And finally, in the end, it would point to nothing or a null node. So what you are given is this head. This is something that would be provided to you. And let's say I want to insert the value a at the head of this linked list. So what I could do is simple. I could create a new node, and this would be initially pointing to null, and I can store this value a at this position. So we would have this node a. After this, what I can do is I can take this pointer that you see right here. I take this and I point it to the head of the linked list. Now the node structure is something like this. We have the node a right here. We have the head of the linked list here, and let's say the remaining list is there, and the head is pointing here. So after that, what I would do is I would take this head, I would remove this head from here, and I would assign the head this. Fine. So that is the idea, that is the logic, and let's write the pseudocode. Pseudocode. So what would the function look like? Function would look like, let's say it has a return type of void, regardless of the language you're using. It doesn't matter. The function name is insert at head. So what you would be given, the head, fine, and the value. So what we do is, let's open the braces. So what we did, first we created this node a, right? Our first job is to create this new node. I can say new node is equal to a new. New is the keyword that creates or allocates new memory, and the constructor for this node, and I could just pass the value a, and by default I am assuming the constructor of node is initializing the next pointer to null. So that's, then what I have to do is assign the next pointer of this node a to the head of this linked list. So then I can do is new node next value is actually equal to head. So I'm making sure that the next of this new node is pointing to the, okay, that's done. And after this, we have this condition before reassigning the head. So what we are left with is to reassign the head. So now head is equal to new node, and you close this function. Now some things I have taken for granted is that what you could do is, rather than returning void, you could do is you could return the pointer, the new head, right? So you can declare the return type as the node star, which would be the pointer of the new head, and after making head as the new node, you can just return the head. So let's say you are given a head HD, and let's say you have to insert a value. So what you could do is you can say HD is equal to insert at head, and you can pass this HD itself and any value, let's say 7. So what would happen is when you would be using the head after this, it would be of the updated list. Okay, so whenever you write a code, the next important question is, what is the time complexity? So the time complexity would be what? Let's look at this. There are no loops, right? So creating a new memory allocation. So this is a constant time operation. Again, assignment is again a constant time operation. Again, assignment is a constant time operation. And let's say return is also a constant time operation. So what this would give us is 4 order 1 operation, 4 times order 1, which is still an order 1. So inserting at head would be constant time operation. So next is the space complexity. So what is the space complexity? We are allocating a new node, so that's constant space 1, and then we are just using the space that is already given to us. So again, it's order 1 space as well. So we can conclude that inserting at head is both order 1 in space as well as time for both of them. So we are actually, if you see, we are actually done with this. Now let's look at inserting at tail or inserting at the end. Again, let's draw a linked list. So there are 2 cases in this as well. So when you implement a linked list, you can implement in 2 ways in general. Either you can only keep track of the head pointer, or you could have both head or a tail pointer. So tail pointer would always be pointing in the end or at the end of the list. So if case 1, if we have a tail pointer, so if we have the location of the tail pointer, that means if I have the head right here, I have the tail right here. And this is exactly same like the previous one, but just a slight difference. So the thing is, if you have the tail pointer available to you, the very first step always is to create this new node, which would be pointing to null. And let's say the value initialized in this node is, so first you initialize your new node. Then to add this at the end of the list, what you could do is take the tail pointer of this, take this tail's next pointer, which is actually pointing to null, and point it right here. And after that, since tail is pointing to the second last element, you need to reassign the tail from here to actually, so tail would point to this new node that you just created. So let's write the code. So again, let's assume this is a void type, insert at tail. So inserting at tail, you would be given the tail node and the value. What is the value? Let's say a, or not just that, value. One more thing I forgot to mention in the previous case, when you insert at head, right? And if you have a tail pointer, you need to do some modification as well. We'll discuss this after we discuss this insert at tail. So a couple of things. Let's start by creating this new node. So open the braces, new node, to new, allocate new memory for this node and this node itself. And for the constructor, let's pass the value, this one. Let me check if I've written the code properly in the previous case. Okay, so in this case, that's not a, but the value. Fine. New node is new node value. And what you do is you say tails next is actually this new node, right? First we've created this node, then we are pointing the next node of this tail to this new created node, and then we need to update the tail value to this node. Now tail is equal to new node. So that is the function. Now there are a couple of things I missed in this and the previous one as well. So let's say if you can figure that out for the time being, let's just move all of this down and let's look at the case where, so I'm trying to get the next pointer from this tail, but what if the tail itself is null? So there is no next pointer, so that would give you some sort of segmentation fault or something like that. So what do you do in that case? Simply you just initialize a check if tail is equal to null. What you do is, or rather than initializing this, you always need to create a new node, right? So let's take this, shift it up. So what you do is you check tail is actually equal to null. In that case, what you do is a couple of things. You say head is equal to this new node, tail to this new node, and then return. So did you see what I just did? In this case, if tail is null, that means the head would also be null, because if tail or head is null, that means there is no node in the linked list. So whenever you add a new node, rather than at the head or the tail, you need to initialize the head and the tail pointer. Assume that head is already given to you as an argument, or you could access this value globally. I have not taken this in the argument right now. Now, how to implement this exactly, we would see in the next video, because anyways, when we are going to implement this linked list, we would be implementing this in a class, and the class, we would have the access to the head or the tail without passing these arguments of head or tail. So if you want, you can just pass the head as well. Fine, the head would be new node and the tail would be new node, and then you return. Otherwise, if that is not the case, then there is at least one element which exists, and therefore we can actually perform this dereferencing of the next pointer. And I can say this tail's next is actually this new node, and finally tail is equal to this new node. So this case we just missed in this one, and as well as in the previous one as well. So inserting at head as well, if you have a tail value, if you also are using the tail, so in this you have to check if head is null, then this new node would also be the tail as well, and you have to do the same if statement and return accordingly. But otherwise the time and space complexity would be exactly same. And for this as well, inserting at tail, what you the time complexity would be what? Order 1, because these are all order 1 operations. So the sum of 5 or 6 constant order 1 operation is still order 1. Let's talk about the space complexity. In this, the space complexity is again order 1, because we are just declaring a new node and that's it. So the space complexity is order 1. So for inserting at head, inserting at tail, both are order 1 operations, assuming you have the tail pointer as well. But in general, tail pointer would not be. So what do you do in that case? In that case, you have to do the traversal. So let's do the traversal. Let's take this as, let's say this is the linked list. So you have the head pointer, right? You have the head pointer. You can just traverse, and you would stop when the node that you're trying to traverse with and the next of that pointer is actually equal to null. At that point, you'd stop. If that node's next is null, that means we are at the last element. Now in this case, we only have the head pointer. We have no tail pointer. So let's write void insert at tail. So when you insert at tail, you would be provided the head pointer and the value, let's say value. Let's open the braces and let's start. So the very first thing is you check head is equal to null, right? If head is equal to null, that means, or even before that, we always create the node first. So let's say new node value. Okay, now you check if head is actually equal to null, right? So if head is null, what you do is nothing. What you do is directly say that head is equal to new node, and then you just return. Okay, because there is no node, so whenever you insert at tail, that would be the head only, and so you have to update the head. Now otherwise, head exists, so let's say temp is equal to head, and while, now we are actually traversing the list, so while temp's next is not equal to null value, what you do is you jump to the next node. Temp is equal to temp's next. So you are traversing the list till you reach the last node. So after this while loop, you would be at the last node, and what you simply do is you say temps next, the next element of the last node of this list is this new node, and you close the function body. Clearly, first you create the new node. As always, you check if head is null. That means that is the very first element regardless where you have to insert. Now what you do is you create a temporary pointer which is pointing to the head, and while temps next is not equal to null, you do this operation. Now observe that we are trying to dereference the next pointer, right? You're trying to get the next pointer of this temp, and at this point we know that temp is head in the very first iteration, and we've already checked that head is not null. If we reach here, head is not null, so temp is not null, so this statement would never ever be wrong, right? Would never ever cause any error. After that, you just traverse the linked list, and after doing this traversal, you just mark this next node as this new node. So this new node would now be at the end of this list. Okay, so that was what? That was without the tail node. And what is the time complexity? As always. Now, let's say the linked list has size n. So what you're trying to do is you're trying to reach the last node, right? So you would travel the whole list. So because of that reason, the time complexity would be order n. Because if you change the length of n to 2n, you would have to traverse 2n list. So that means that this algorithm depends on the size of the input, and not just depends, it depends linearly. So that is why time complexity is order n. What is the space complexity for this? Space is again order 1 because you're just declaring a new node. So that was the time complexity and the space complexity. Okay, so after all of this, what you need to keep in mind whenever you are doing this is that you need to track if the pointer is null, what you have to do in that case. Because if you have the list, you know what to do. But if there is no list, you need to keep that in check. So with this, we have completed inserting at tail or inserting at end. Now let's do the most interesting or the difficult part, which is inserting at any position. Fine. So this depends what you define by position. So let's say you have a linked list like this, and for this example, let's keep the length of the linked list as finite. We actually know the length of this linked list. Let's say you have to add a new element at position 3. Now this could mean one of the two things. Either you insert after the third node, right? Or this could mean that after inserting, the new node should be at the third position. So if I mean position is equal to 3, there could be two cases. That means either the node that I would be inserting should be the third node or should come after the third node in this list. And accordingly, you can just modify your implementation. And for this example, what I would be taking is I would be saying that it should be after inserting, position should be 3 of that new node. So position starts from 1 to the number of elements in the list. So that is the idea. So let's think about this for the moment. Let's again take position as 3. So what I could do is, what I'm trying to do is when I insert the element, this element should be the third element in the list, right? So let's create this new node as A, and next is pointing to null. Now what I could do is I want to insert it at this position, so that after inserting, this is at the third index. So what I could do is I could take this link and assign it to this node, and I could take this link and assign it to this node. And so you see, we are actually going like this, and after insertion, we are at this node. Now we first pointed this to this node, right? And the location of this node is where? To get access to this node, you need to have the location of this node. So let's traverse the list to this node. Fine. First, when you traverse the list to this node, what you could do is you could get the next pointer of this, and you can assign the next pointer of this node A to the next pointer of this node. So you would have this link, and after that you could just update the next pointer of this to this A node. That is as simple as this could be. Now we have to figure out how to reach till this node. So we have to reach the second node to insert at position 3. So for inserting at pth position, we need to be at p minus 1. And if you want to be at p minus 1, you have to, starting given this head, given this p minus 1, or in this case for reaching the second node, you have to do one jump, right? So since you are jumping one time, so given the pth position, you need to iterate or go to the next node p minus 2 times. I hope that is clear. Okay, so that is the idea, and I am assuming that position is within the length of this linked list. The position is less than equal to the length. That is the idea. So let's write the code. So insert anywhere or insert at position. So you would be given the head. You don't need the tail pointer in general. So you need the head, you need the value, and you need the position as well where you are going to insert, right? So let's do that. So what you do is you start the braces, and first you check if position is equal to 1. So we want to add this node at the head. So what you could do is you could just call insert at head. You can pass the value head node and the value, and you can just return. Fine, that's one thing. Now next what you have to do is a couple of things. You need to traverse. So given the p, you need to jump p times, right? P minus 2 times. So that is what we are going to do. So let's take a temporary node as head, right? And what I could do is, rather than for I is equal to 1 to what? P minus 2. So we are jumping p minus 2 times to reach this node. So if p is 2, so that means we are not going into this for loop at all. What you could do is temp is equal to temps next, and I'm assuming that the length is within this range. And on second thoughts, let's do this +1, because if I say if position is exactly the length of the linked list, it would, after insertion, it would be at the second last position if you think about it. So I need a way to actually add it to the end as well, right? So for this one, we would be actually inserting at tail. So after doing this, we would have a temp node, right? And if this temp node is equal to our temps next node is equal to null. What does that mean? So let's say for this case, we have how many nodes? 1, 2, 3, 4, 5, 6, 7. For the moment, forget about this. So we have 7 nodes like this, and let's say my position that I've given is 8. So in that case, how much jumps I would make? I would make 6 jumps. So 1 temp would go here, then 2, 3, 4, 5, and 6. So temp would go here. So if I'm saying that I need to insert at the position 8, and that means I'm at the last position of the node, so temps next is null. That means I have to insert at tail. So if temp next is equal to null, what you do is you insert at tail, but you would be doing this with the head pointer itself and the value. Or rather than, since we have already reached the end, what I could do is I can just say that temp next is equal to new node and then return. Let's, because we are already at the last node, so why call this function again? So in that case we return. And let's see if I have created this new node or not. So we have not created this new node. Again, if position is at 1, you can do this in order one time. So let me just create this new node is equal to new node a, or given value val, and we are going to use this new node, right? You add that to the last position. Otherwise, if that is not the case, neither it's insert at head nor it is insert at tail, that means we are somewhere in the middle. And then it's very simple. Whatever the temp is, take, what you do is first you take this new node and you assign the next of it as temps next. So by this, what I mean is you are assigning this link to this. So new nodes next is actually equal to, this would be temp, so temps next. Okay, after this, because we have assigned the temps next to new nodes next, what I can do is I can say that temps next is actually this new node, and this is where we return. So forgive my handwriting for the moment. but that is the idea. So basically, if you are inserting at any position P, you need to reach, let's say if you're trying to reach position P, you need to reach P minus 1th node to access the next pointer. And to reach P minus 1th node, you need to jump P minus 2 times, right? So this is actually the code for jumping to the next node. So that number of nodes we are jumping, and through that we are at the node which is just before P. So now we insert an element, and so the new node that we inserted would be at the P position. Okay, as always, what is the time complexity for this? The time complexity would be order n, because if in the worst case we reach till the end of the list, we have to iterate through the whole list. So in the worst case it would be order n. The best case would be order 1, but asymptotically when we see, it's always the worst case analysis. Space complexity is what? It's order 1, because we're just initializing some new space through this new node. Fine. Now I know that you're smart enough, but this new node is a single variable. This new is a keyword that is used for memory allocation, and this node is the class node with the constructor having the value val inside it. Anyways, so that's this. Now let's discuss the time complexity, space complexity of all of the things that we have discussed. So how do I do this? Okay, insert at head, insert at tail, insert anywhere, or insert at position. Now I am considering the case where you only have the head and no tail node, because that is what usually happens. So inserting at head, time complexity is order 1. Inserting at tail be order n, because you have to traverse the whole list, and insert at any position. In the worst case, if you insert at tail, that is why this is order n as well. And if you observe, space complexity for all of them is order 1. Now for if you have a tail as well, let's say if you have the tail pointer, let's do that. Let's say with tail, without tail, and tail. If you have a tail pointer, it's order 1. This is also order 1. If you don't have without tail, WT stands for without tail, so this is also order 1. This is also order 1. So without tail is order 1, order 1. With tail, order 1, order 1. In this, there would be change in this. Now insert at tail, without tail, and with tail. If you have the tail, it would be order 1, and without tail, order n and order 1. Now this as well, although we've not discussed this, but because we are traversing the list in this one, and it could be at any position, so with or without tail, the answer would be same. It's order n, order n, order n. Oh sorry, this is order 1, order 1. So in all the cases, this is order 1. In these cases, this is order n. These cases, it's order 1. Yep. So that is the whole idea about inserting in a linked list. It's quite straightforward. Video is quite long, so the coding part, as I said earlier, would be in the next video, so be sure to check that out. In that, I would create the whole class, and the implementation might differ slightly because the way that the language behaves and whatever I would be thinking. So that's the thing. We would implement that to a class. We'll implement insert at head, insert at tail, insert at position. So be sure to check that out, because when we're trying to delete an element or search an element, we would be using this same code. So that you don't have to revisit this again, be sure to check that out. So that was the video. Hope I was able to teach something to you. Hope this was good enough, and I'll see you in the next video. Bye.